Okay. Something's moving in some direction, some velocity v. And it's accelerating only in this direction. We assume we've got a coordinate system here. X in this direction, Y in this direction. I is a unit vector in the X direction. K is a unit vector in the Y direction. Okay? Then the velocity is completely equivalent to E sub x I plus V sub y j. And we then put a little mark on the V saying that, okay, we don't have V anymore, we have a V sub xi and a V sub yj. Okay? In this case, there is no acceleration in the I direction. Okay? So, AX is just a zero vector. Okay? Because all the acceleration's in the Y direction. A is just negative AJ. So, the motion is sum V sub 0x times, well, V0x plus AXTI which is V0xi and of course at whatever time this is, okay, let's just say this is the particle at if this is state at time t, then okay. Now, since we have this now at time t, we can call this v of t. We can call this vx of t, and I didn't leave room to put my t in there, but there it is, it's real tiny. And a of t is just negative aj, okay? So, V naught x equals this. So V naught x is just some number that matches this, is constant. I want t to be a variable. So I'm going to call this v of t naught, and all these t's have a 0 on them too. I'll put a 0 on this one. And I probably should have. Now that's just a formal way of saying, because toss this piece of chalk, it would keep moving in that direction at the same velocity, assuming we neglect our resistance, simply because gravity is acting downward, has no effect on velocity in that direction. And that's the main takeaway here. Of course, you want to understand the formal way of doing this too, because you're going to need to do that sort of thing in some of the problems. Okay?
I was going to say, like in space, essentially, where it would just never stop, but then you don't have gravity moving down.
Yeah, well, in space, of course, you do have gravity if you're anywhere near a planet or a galaxy or any kind of matter. Okay?
Yeah.
But if you were in totally intergalactic space where all the galaxies are so far away that they exert no discernible net force, then you would ideally move in the same direction at the same speed forever. Okay? So that's one of Newton's laws, which you're probably familiar with. Okay? Newton's first law, an object in motion remains in motion, same speed, same direction forever. Unless a force is exerted. Okay?
Right.
So you got to have a force to change speed or direction. Okay?
Yeah.
So we'll state that more formally, but this is it. There's no force in this direction. We're just looking at a projectile. If I toss this chalk to you, which I won't do because you got your backpack and stuff, I don't want to hurt you. You're gonna, it's accelerated downward, it's not accelerated in the horizontal direction, just like the ball in the experiment you did Friday, right? So we're just generalizing this a little bit, okay? So you can think of the ball. Of course, doesn't have an upward velocity, that's okay, you know, give it any velocity, horizontal velocity. Velocity with both components are straight down because it did drop it straight down. Okay? So all this applies, and this is just a formal way of stating that intuitive idea. Okay? So the y component of the acceleration, of course, is constant in the j direction. So your motion in the y direction. And I've been a little sloppy with my notation. So we call this Vx of t. This is t naught. This is any time that we choose to observe the thing and start our clock. Our clock could have started at another time. So basically then we have Vx of t equals Vx of t naught times I, so that x of t is x of 0 plus Vx of t naught times t times I. You just integrate this. Your integration constant will then be whatever the position is at time 0. And that's something I hope you're familiar with. You've done that for quite a while. Okay? Now, y of t and I'm going to do Vy of t. In this case, would be y of 0 minus at times j. That's just your y velocity. And an integration tells us that y of t and it's going to be x and x. And y are vectors. Y of t is an antiderivative of this, which is should be y of 0. I started to do something else. It's Vy of 0, obviously. Okay? And y of t then is y of 0 plus Vy of 0 t minus 1/2 at squared times j. Okay? And your position in space, and actually we're just looking at a position in the plane. This was moving, if something was moving 3 directions, you just have a z of t, and you'd have a rule for z of t. Okay? Right now we're just going to consider the plane. So motion in this plane is characterized by this. Okay? R of t is x of ti plus y of t. X of t plus y of t equals what? X of 0 plus Vx of t naught t times I plus y of 0 plus Vy of, and I made this t naught, right? Okay? That would be your position function. Okay? So let's apply this. With a velocity that I'll call v sub 0 times I. Okay, well, what's its position function? going to find a valid position function. R of t. Well, I'm not going to drag it out of you. The first thing you want to do, because it might not occur to you, but it'll start occurring to you, and maybe it does already, we got to know when t equals 0 is. So we start by first specifying when we start the clock. Maybe you started the clock when the ball started rolling down the incline. Okay? And it's a constant incline, you have pretty much a constant acceleration. Okay? But of course, at the instant the thing reaches the end of the ramp, that constant acceleration motion no longer applies. It's a different constant acceleration motion where you're now in free fall. Your acceleration is the acceleration of gravity. Okay? And we usually use, for most calculations, we're going to use 10 meters per second squared instead of 9.8. Okay? Just because calculations are easier, and 9.8 is only 2% less than that. And that 9.8 is not an exact constant. It varies from point to point on the Earth. And there aren't many points which is as low as 9.8, actually. It's like 9.81 something. Okay?
Where is it different?
I'm sorry?
Where is it different? Like different?
I'm sorry.
Where is the gravity different around Earth? Like different sea levels, or?
It's different at the bottom of the hill here than it is at the top of the hill because we're further from the center of the Earth.
Yeah, that's what
And also, we don't know what's under us. We've got a big old cubic mile of iron right under our feet. And if we do, I think geologists would have noticed that. But if we do, then it's going to be stronger than if it wasn't there. And we can calculate that easily using Newton's law of uniform gravitation, of universal gravitation. Okay? And I say we can calculate it easily. If it's a sphere of iron, yeah. If it's a cube of iron, it's not so easy. But you can do it by numerical integration. Okay? Okay, so anyhow, we want to specify when we start the clock. A little bit of digression into why we use 10 meters per second squared for G. Because it's a good ballpark. And once you have the calculation scheme and get the answer for 10, if you understand proportionality, which nobody does, you can easily adapt all your results to whatever the deviations are from the 10. Okay, so anyhow, specify, when do we start the clock? Well, just for this problem, we don't care how the ball got there, okay? We don't care that if it was rolling down an incline, it had to change direction, so it'd be in the horizontal direction before we roll off the edge, right? So it's probably not a pure straight ramp, unless somebody gave it a push. So we don't care about that at the moment, okay? But sometimes we do. And, you know, another time we might want to, another place we might want to have our clock at 0 is when it hits the floor, in the case of our example, okay? Which means that it rolled off at a negative time. Of course, clocks don't run backwards, okay? So we wouldn't literally start the clock at that point. It wouldn't give us much information. But we can still set t equal to 0 at any point we want. And if we get a negative result, we get a negative result. It just means that, well, this is what happened before it was there, assuming it was still in free fall. Okay? And that's going to be important. Okay, so anyhow, specify when we start the clock. let t equal 0 at the instant ball loses contact with, what do they call the thing? Incline. Then, well, R of t equals what it does. It also we're going to let t naught equal 0. And we need to have a t naught to use this expression. We're going to let t naught equal 0 because that's where we know the velocity. Okay? So, r of t is x of 0 plus vx of t 0 times t times I plus y of 0 plus vy of t 0 minus 1/2 whatever the acceleration, magnitude of the acceleration is. Okay? And that equals, what's x of 0? Well, we haven't decided where our coordinate system, where the origin of our coordinate system is. Okay? So we're going to implicitly assume that we have a horizontal vertical coordinate system with the origin at the point where the ball leaves the incline. Okay? Could have stated that earlier, but I actually consciously decided to let it come up here. But I'm not going to be able to write it down. I'll write it down after we've used it. Okay? In that case, if the origin of our coordinate system is at the position where the ball leaves the incline, then what is x of 0? Well, where's the ball at t equals 0? I'm sorry? It's at the end of the incline. And what's that in our coordinate system?
0, 0, origin.
That's the origin, yeah, 0, 0. Okay? So it's going to be 0 plus vx of t0. What's the x component of the velocity at time t0?
0.
It's what?
0.
No. No. Wouldn't
Oh,
leave the incline.
velocity.
Okay?
We don't know.
It's v naught. Well, v naught I. Right? Now we could formally say, okay, at t equals 0, this is 0 also. Uniformly careless here. Okay, v naught t, right? At t equals 0, well, we know y equals 0 as well, right? So y0 has to be 0 because all the rest of this is 0, right? The only way all this is going to be 0 is it has to be, because we're at the origin, t equals 0, is for y of 0 to equal 0. Okay? So x of 0 has to be 0 so that this whole thing has to just equal v naught I. Okay? And maybe I'll do this a little differently than I was going to. I can write it out this way. R of 0 equals v naught I. Right? R of 0 equals x of 0 I plus y of 0 j, because every other term in this entire expression has a t on it, right? Then r of 0 doesn't equal v naught I, r of 0 equals 0. R of 0 is this, R of 0 is this, so x of 0 equals y of 0 equals 0. What I want to apply is this condition, right? So d of 0 equals dr dt, which is simple derivative has to equal v naught I. So Vx of t0 equals v naught, Vy of t0 has to equal 0. Okay? Because the j component of this is 0. There's no j component in the initial velocity. Now in a minute we're going to do one we do have a j component because we want to analyze what happens when that ball does roll off an incline without changing its direction. Its direction begins changing instantly after it leaves the incline, but that direction is the direction of the incline at the instant the ball leaves. Okay? So, and I really need to, okay. Well, we're going to have to stop for a minute. I thought I had a clean board there. I'll position this and then something else will continue.